Okay, we're back with changing area. So now we've talked about changing B field. Now we're going to talk about changing the area. Okay. A wire is bent into three sides of a rectangle as shown in the diagram. The wire is immersed in a uniform magnetic field B that is directed out of the page. A bar is set on the two parallel sides of the wire to create a complete rectangular circuit of height L and width X as shown in the diagram. The bar can be pulled to the right by external force so that the bar travels with speed V. So basically it's creating a square here. Okay, and this bar can actually move left or right. In this case, it's going to move to the right. Okay, when the bar moves the area through the rectangle circuit, and therefore the flux increases, right? Does that make sense? Because if we increase the area, we're catching more of these magnetic field lines. Okay, use Faraday's law to derive an expression for EMF induced in terms of V, L, and B. Okay, it's actually not a hard derivation. If you remember that flux is equal to B times A, okay? And we don't need to worry about the cosine theta because, again, that will resolve out to 1, okay? And we know that the area, how can we find the area of this rectangle? Well, we're not given this right here, so there actually should be an additional parameter here that we're going to define as x, okay? And I know it's not like in our permitted variables, but you're going to see that in a second that we don't need it actually, okay? So this would actually give us b times L times x, okay? Okay, now if we're looking at delta flux, what's actually changing here, right? It would be delta parentheses BA, or BLX, right? But only one of these things is actually changing, and it would actually be L, right? So it would actually be B delta L X. Okay. Oh, so I'm so sorry. It should actually be delta X, right? Because it should actually be L is not changing, right? L is the vertical, X is the horizontal. That is what's changing, right? Okay. So it should be BL times delta X, right? So then what you're going to do, okay, is then you're going to plug that into Faraday's law, right? Delta flux over delta T, okay? And you'd plug in this equation right here, BL delta X over delta T. Now wait 1 second, okay? Look at that. Look at the equation that we just made. Do you notice, right? We have delta x over delta t. Huh. That's a quantity you should know. That's velocity. Okay. So this actually will end up being b times L times v. Okay. And that's actually right there. That's the whole equation. That's all you need. It's epsilon equals b times L times v. That's it, right? Okay. Nothing too crazy about that. That derivation is pretty straightforward, right? Okay. Use Lenz's law to show the direction of the induced current around the rectangle as the bar moves. Okay. Well, as the bar moves, what's happening to your flux? It's increasing, right? So we would need to use our left hand. Okay. Okay. B field is going out of the page. Okay. And you should see that the current is going around this way. Okay. Okay. So it would go clockwise. Okay. Okay. Explain the direction of the induced current in terms of the free charges in the bar. Okay. What do I mean by free charges in the bar? When I say that, we're talking about the charges that are in the bar that are free to move around. Okay. Charges in bar free. That are free to move around. Okay. And so what's happening, right, is if we envision this scenario in where we have here's the bar, right? And then here's your magnetic field coming out of the page all around it, okay? Then what's going to happen, right, is let's say that we have a proton in the bar, okay? The charges, okay? They're flowing through the bar, right? The charges are moving downwards, right? The current is flowing downwards, right? We're going to use our right hand rule for the wire, okay? The current is flowing downwards, okay? And and so this is moving to the right, okay? This is basically the same thing as a charge moving to the right in an out of the page field. Oh, sorry, why did I say F? I should say it should be V right here, okay? So when I do my right hand rule, they have a velocity going that way, okay? Can you see this a little bit, right? They have a velocity going that way. The B field's out of the page, so the charges feel forced downwards, right? Okay. So the positive charges, okay, positive charges in a field coming out of the page feel force downwards. Okay? And if the positive charges are forced downwards, then that means that they're going to go down and then around, and that gives you the same clockwise current. Okay? Okay. What is the strength and direction of the magnetic force acting on the bar as it moves? There's a couple of steps to this. Okay? The first step is to get the current. Okay? We need to get the current first. Okay? And we'll do that with epsilon equals IR. Okay? And if you recognize, okay, that we don't know that we actually already have an expression for epsilon, okay, we got it way earlier up here. So I'm going to draw a big line here, okay, showing that we're going to go from this, we're going to plug that into that equation, okay. So now we have, this is going to be BLV, okay, equals I times R, okay. Then we can get an expression for I if we just divide R on both sides. You end up getting I is equal to BLV over R. And that's the expression right there. Okay, that's for the current. Okay. We need the current because we need it for the force equation. This is essentially, because the bar, we're going to treat it as a current carrying wire. Okay. So step 2, okay, is to get the force on the current. And we're treating it, again, as a current carrying wire, okay? So if we take F equals ILB, okay, we don't need to add on the trig function at the end there. We'll just do ILB, okay? And we replace this expression for I with what we just got over here, okay? Then you're going to get this really big, long equation, okay? In this case, L right here is actually going to be capital L, okay? So we're going to change that to capital L. But what this is going to turn into is it's going to be BLV over R times LB. And when you simplify that a little bit more, you end up getting B squared times L squared times V over R, okay? That's all you need, okay? That's the force right there on the wire, okay? That's an expression for that. Okay. Okay. All right. All good on that one? Okay. The diagram shows a single circular loop of radius r placed halfway in and halfway out of and into the page magnetic field B. Resistance of the loop is r. Suppose that the loop is moved so that an average counterclockwise current. Ooh, counterclockwise. That's an important word right there. It says that we want a counterclockwise current induced in the circle. Okay. It's counterclockwise, and B field is into page. Okay? So in which direction must the circular loop move in order to induce a counterclockwise current? So which of our hands is going to give us counterclockwise if we point our thumb into the page? This right here is going to give us a clockwise current, so that's not going to work. So our left hand is going to give us the counterclockwise. That's what we want. So we're using our left hand, okay? That means it's going to be an increasing into page flux. Okay. So it would need to go, so loop moves right into B field. Okay. In terms of RB, R, lowercase r, B, capital R, and I, to calculate the time it takes for the loop to move the half circle width necessary to induce the average current indicated. Again, another two-step problem, okay? We will need to first off find the delta flux, okay? Which would be, what's changing here is actually the area that's being exposed to the B field. So initially half the area is exposed to it, okay? Initially half the area is in the B field, but we're ultimately going to move the other half into it as well, okay? So it would be B delta A, okay? Now, delta A, what's the change in area going to be? Well, and we already have half the circle into the field, right? The equation for area of a circle is pi r squared, but we only need to move the other half into it. So initially we start with half the area in it, but we're going to get the whole area in it. So it's just going to be 1/2 pi r squared, okay? Because half a circle enters B field, okay? So then this expression becomes B times 1/2 pi r squared, okay? Okay, so that's the expression for flux, okay, for change in flux, okay? Now we just need to plug it in to the epsilon equation. Epsilon is equal to delta flux over the delta t, right? Okay, so then when we plug everything in, we're going to do B times 1/2 pi r squared, okay, over delta t, okay? And you should also recognize, right, that we actually can figure out what the current is, right? We're trying to figure out so the time it takes, right, to induce the current I. We can't have the current in here. Epsilon is not on our permitted variables, but we can express epsilon in terms of our permitted variables, right? So let's take that expression and plug it in for epsilon up here. So you end up getting this new expression where we're setting this whole thing equal to I times R, right? Okay, now you just need to get delta t by itself. Okay, what I'm going to do first is flip both sides. I'm going to flip the fraction on both sides, right? So this gives us delta t over b times 1/2 pi r squared, okay, equals 1 over IR. And then all I got to do is multiply the whole denominator on the other side, okay? That gives me delta t is equal to b pi r squared over, and all I'm doing here is I'm taking the 1/2, I'm moving the 2 to the denominator, okay, because that's perfectly fine, okay, 2 IR. Okay, and I believe, yeah, everything's in terms of what we're permitted to have, so that's a good derivation right there. We're all good on that one, okay? Okay, so there's that. Nothing too crazy, okay? Don't be too scared about that, okay? The next example on the next page looks daunting, but it's really not, and I'll show you why, okay? There's a question on the web assignment that's just like this, okay? The loop here, okay, we have a rectangle loop, has width of 4.4 meters, height of 0.2 meters, resistance 0.1 ohms, travels with constant speed 4 meters per second. Loop enters a region of magnetic field where B is equal to 2 teslas, okay? Okay, that's a lot of information to take in. It's constant speed. B is equal to that, directed out of the page, okay? The loop passes through the field region and eventually exits. Determine induced EMF, induced current, and magnetic force. Guess what? For this whole problem, we only need to do 3 calculations, okay? Only 3 calculations. I'll show you why. Induced EMF, you know that induced EMF is equal to delta flux over delta time, right? And then we need to figure out delta flux, right? I want you to consider this, okay? Initially, as the loop is entering the field, initially, the loop has its right end right here. Okay, this square, this rectangle I'm drawing in blue. Okay, initially this is where the loop is. Okay, and at the end of everything, this is where the loop is going to be. Okay, it's going to be fully in the field. Initially, how much area is in the field? 0, right? Then at the end, how much loop is in the field? All of it, right? So the change in area, okay, the change in area is the whole thing, W times H, okay? So then the change in flux would be, B times the change in area, which is just BWH, okay? Plug that into the epsilon, and you get epsilon equals BWH over delta t. Now, another thing to understand is that when the loop, right, when the loop is entering the field, how much does it move You know, from when it's just about to enter the field to just after it enters the field, it actually moves a distance of 0.4 meters. Okay, does that make sense? Because it's traversed its width. Okay, what that means is that if we know that, we can then intuit this idea that width divided by delta t is actually just position over time or displacement over time, right? Hey, wait a minute, what's that? That's velocity, right? So we end up getting bhv, okay? And that is the equation that we need, okay? So then plug everything in. B is 2, H is 0.2, and V is 4. Now, if you actually plug everything else in this way, right? I don't think you have. Oh, sorry, you're not given delta t, okay? But you wouldn't be able to plug it in here, so that's why you have to do W over delta t, okay? When you plug everything in here, you should get 1.6 volts, okay? 1.6 volts for the induced EMF. Now, what you could then do is actually use this epsilon to work backwards and figure out what delta T is, but the problem's not asking us to do that, okay? So I would not be too concerned about that at the moment, okay? Induced current, okay, the induced current, okay? Well, you know that induced current is epsilon equals IR, right? Okay? Epsilon equals IR. So then what we're going to do is we're going to just take our epsilon value, 1.6. We don't know the current yet, but we do know the resistance of the wire, okay, which is given to us as 0.1 ohms. Divide 0.1 on both sides, you get current I is equal to 16 amps, okay? Now, to figure this out, right, as we're entering the field, our flux is increasing, so we have to use our left hand, and it's going out of the page. So as we go, you're going to see that it's going to go clockwise, okay? Okay, and then finally, okay, magnetic force, okay, is going to be, we would use the right-hand rule to figure out the direction, which we'll do here in a second, but you should recognize that the force, okay, is ILB. Now, for L in this case, okay, oh, sorry, I should use capital B because lowercase b is different. For L in this case, we're actually just going to use H. Why are we using H for L? And I'll tell you why that is, okay? Why are we using H for L? It's because if you notice, right, even though these horizontal parts of the wire are in the field, their forces are actually going to cancel each other out because the current is going opposite directions, but the B field is the same direction. So they are actually going to go opposite directions of whatever they are of each other, so it'll cancel out. The only part that's left is going to be this part right here, okay? Now, when the other end of the wire enters, then yes, it'll cancel out as well. But as it's entering, right, it will still feel a force only on this horizontal segment that is H, okay? So then I'm going to plug in all the numbers, and I'm going to do F equals the current, which is 16. The H in this case is 0.2. The B field strength is 2. We plug all of that stuff in, and you end up getting I believe it should be 6.4 newtons. Okay. 6.4 newtons. And the direction of the force, we would use our force right-hand rule. Okay. So we would use our right-hand rule. You can do it with the current, okay? The current is going clockwise, so it's traveling down as it enters, okay? B field's out of the page. Our force is going to the left, okay? So we would mark that down here as the force going to the left, okay? Okay, now here's where it gets fun. In the middle part, where the loop is completely in the field, guess what? It doesn't matter where it moves in the field. Up, down, left, right. It's moving to the right now. It doesn't matter. As long as it's completely in the field from its starting to ending position, there is no change in flux, right? Because the area nor the B field are changing, okay? So delta flux is equal to 0, so EMF should also be equal to 0, okay? Wait a minute. If you have 0 EMF, then how much current must you have? Right? Well, epsilon is equal to I times R, and I is equal to epsilon over R. Wait a minute. If epsilon is 0, okay, then current must also be 0. Huh. Okay, so then there's no current being induced into there. The magnetic force, wait a minute, is F equals ILB, okay? Wait a minute, but I is equal to 0, we just found out, so there's also no force on it, okay? Interesting how that works out. As the loop exits the field, everything that we just solved is very much similar. It's very similar to everything that we just solved. It's just now some of it gets a little bit flipped. Okay. Guess what? The delta A, B times delta A is is the exact same for exiting the field as it was entering the field. Okay. All of these things are the same for exiting the field as it was entering the field. So the EMF, okay, is actually going to be the same. Okay. Flux and delta T, same as first column, okay? So epsilon would also be equal to 1.6 volts, okay? The induced current, is that going to change? Well, epsilon and R, same as first. However, but flux is decreasing, okay? So if flux is decreasing, now we got to use the right-hand rule, and you'll notice that it's actually going to go the opposite direction. It'll now go counterclockwise, okay? But the induced current magnitude is the exact same. It's still 16 amps, okay? The magnetic force, again, current is the same, okay? So I, L, B are same as first column. So F would also be equal to 6.4 newtons, okay? What direction is the magnetic force acting? Well, it would actually act in the same direction, okay? Because the current is now flipped, so it's going counterclockwise. So this segment that's still in the field is going down, okay? Would be going down. Field going out of the page, it's still acting to the left, okay? So it would still go to the left, okay? You can also say force opposes V, okay? And it still does that, okay? All right, that's that section, all right? Have fun. Don't have too much fun, though.